Hi everyone, welcome to the third experiment. The objective of this experiment is to display the decimal equivalent of the sum obtained from a 4-bit adder on 7-segment displays. So from a functionality point of view, we need to write a Verilog module that should take two 4-bit inputs, say A and B, and this Verilog module should generate an output so that we can connect two 7-segment displays in the output. We know that if we are trying to add two 4-bit numbers, the maximum value of the sum would be 30. The maximum values of each of these inputs can be 15. So the maximum sum is 30. So it's a 2-digit sum. That means we will need two 7-segment displays, one for each place. So let's say one is for tens place and one is for units place. The Verilog module should be such that given these two inputs, there is a corresponding 7-segment display combination that is generated, which will be displayed on these two 7 segments. So for example, if I take number 0, 1, 1, 0, that is 6, and say 0, 1, 1, 1 and 7. What I want to display in the output is the sum, which is 13, and this is how it should appear like. So 1 should appear on the tens place in one 7-segment display, and 3 should appear in the other 7-segment display representing the units place. Or say I give 13 and 1, 0, 0, 0, that is 8. So the sum is 21 and it should appear something like this. So 2 appears on the tens place 7-segment display and 1 appears on the units place. So how will we make the connections here? Of course, we'll be using the pink board, and we know that we need to connect two 7-segment displays. So we'll take a breadboard and connect these two displays next to each other. And since there are two of these displays that we need to drive now, we will have to use both the peripheral modules, PMOD A and PMOD B. So for example, PMOD A deals with the units place and PMOD B deals with the tens place. This is exactly how we have done this in the previous experiment where we used PMOD B. Now, how do we give inputs? We know that there are 4 buttons on the pink board and 2 slide switches, right? But this time we need to give 8 inputs because both of our inputs are 4-bit each. This is where we'll bring in another hardware module, which is called the RPI module or RPI module. This module is also manufactured by Xilinx, TUL, and as you can see, it has 8 switches and 4 7-segment displays. So in this experiment, we'll only use these switches, and since there are 8 of them, we will use the first 4, switch H, G, F and E, to give input A, and we'll use the remaining 4 to give input B, each of which are 4-bit long. So from left to right, we are going from MSB to LSB for both the inputs. So this RPI module or Raspberry Pi module perfectly fits onto the Raspberry Pi header, which is there on the pink board, right? So this is how we will make this connection. And as you can see that since we now have 2 hardware boards, right? So when we are defining the constraints on Vivado, we will have the XDC file of the pink board as usual, but we will also have an XDC file for the RPI module, both of which we will have to update while updating the constraints. So this XDC file for RPI module will be shared with you. And on that file, we will need to define the input boards. Now speaking of the Verilog modules, we know that we are making a 4-bit adder, so we will have a full adder module and not just one, but we will have 4 instances of this full adder module to create a 4-bit adder. Till this part you have already done in the previous experiment. So we know that the 4-bit adder produces a 5-bit output. One is the carry and then remaining 4 are the sum bits. Now the task now is, since the sum has to be displayed on 7-segment, we not only have to first convert this binary sum into a decimal number. Once we have the decimal number, we also need to split both the decimal digits, and then corresponding to each of these decimal digits, we need a binary code or rather a BCD code. Right? So for example, if I was trying to add 1010, that is 10, to 0011, which is 3. So it should generate 13. So we will now need the module for BCD to 7-segment decoder, and not just one. We will need 2 of these, one for each of the units place and the tens place. Now if we were simulating this and we write a test bench. So in the larger picture, that test bench actually becomes the top level module, where there are instances of all these individual modules which are placed within that test bench, right? So the inputs are these two 4-bit numbers A and B. They are added up and the sum is first converted from binary to decimal. Both the digits are split and corresponding BCD code for each of the digits is created. Both those individual codes are then fed into BCD to 7-segment decoders that should eventually give us an output, which is nothing but a 7-segment display combination for each of those 7 segments, right? So for the example that we took for the number 13, in the last stage, the 0001 should be converted through BCD to 7-segment decoder and light up LEDs B and C in the tens place, and this number 3 after BCD to 7-segment decoding should light up A, B, C, D and G to show the number 3. Right? This is what we want to be as the final output. The objective of this block diagram is just to give you an idea of what all modules you will have to write for each of these stages and how they should be instantiated in the test bench and in the final code. Now let us look at the Verilog code. So I have created a project on Vivado and I'm creating all the modules in one single file which I'm calling add_display.v. So the full adder module and the 4-bit adder module, these you have already gone through in the previous experiment. As the next task is to convert this from binary to decimal, what I have done here is a very brute force kind of a code which actually does not calculate binary to decimal conversion by multiplying each of the digits with 2 to the power 0 or 2 to the power 1 and so on. It is just a very hard-coded way of writing the corresponding decimal equivalent. But what I would like you to do in this experiment is to write a proper code that does that conversion, right? That means the LSB is multiplied by 2 to the power 0, then the next significant bit is multiplied by 2 and so on. Right? So make sure that that is the kind of binary to decimal code that you write. The input here is a 5-bit vector and the output is decimal. Now since eventually I also wanted to split this into individual digits, right? That is the ultimate objective. So here what I have done is, in that process of writing the corresponding decimal numbers, I have also written individual tens and units places. Okay. In your case, please write another function that takes your decimal output and then splits those digits up. I have taken a shortcut here, but you should please write a code that does the mathematical computation, right? So for example, if I'm looking at, say the sum is 00101. So here I know that the units place is, so this corresponds to the number, decimal number 5. So this 5-D5 basically means that it's a 5-bit representation of the decimal number, D for decimal number 5. So I'm just saving this decimal number here in this variable, and I, at the same time, for this combination, I know that this should be represented as 05, right, in the 7 segments. So the tens place is 0000 and the units place is 0101 corresponding to 5 and so on. So I know that this can go up to 30. Know that there is this carry in which we take as 0, right? If that carry in was also 1 in the 4-bit adder, the maximum sum can actually go up to 31 in that case. And then there is this condition that is just to show what will happen if it's an invalid case. So once we have the decimal number and we also have individual digits, next task would be to write the function for BCD to 7 segment. This also we have already written in the previous experiment. Know that this particular combination is for common anode 7 segment displays. In this experiment, in this video particularly, I am still using both common anode SSDs. If you have common cathode SSDs while doing this experiment in the lab, please make suitable changes to these codes. Right? So zeros become 1 and 1 becomes 0. This next module called display add simply aims to create the combinations, the 7-segment combinations for the 2 digits. So you can see that I have taken inputs as those 2 individual decimal digits from the previous module, and the output for these modules will be the 7 segment display combinations for the tens place and for the units place. See that this is a 7-bit vector because the 7 segment display has 7 LEDs, right? So going from right to left, we have combinations for A, B, C, D. This is something that you should know. For example, if you're looking at this code, right? You see it says 11110000. Going from right to left, these are corresponding to LEDs A, B, C, D. So A is 0, B is 0, C is 0, D, E, F and G. These are all ones. What this means is that A, B and C will be on and the remaining LEDs will be off. So if A, B and C are on, you know that it will be showing us the decimal number 7. Okay, because this is for common anode. The point I'm trying to make here is that looking at LED combinations, you are going from right to left. So in this particular module, we create 2 instances of this function of BCD to 7 segment decoder, and we call these sub modules as tens underscore or ones underscore. And what this should essentially do is take the BCD input, right? This is the binary combination corresponding to the BCD input, and generate the 7 segment combination, which is a 7-bit output. This last module is your main module where you actually create instances of each of these modules that you just wrote. Here the input are these 4-bit binary numbers. The outputs are 7-bit 7 segment combinations, one for the tens place and one for the units place. Now since sum and carry are intermediate connections here, they are all defined with the keyword wire. So are the decimal combinations, the tens place and the units place. Then we call the 4-bit adder. So first we instantiate the 4-bit adder to create the binary sum. Then we instantiate binary to decimal, take this binary sum, and the output of this particular module, if you recall, if you scroll up and see, was to give the decimal output and also to give the tens place and the units place of this decimal sum. Then we call this last function decimal and addition, where the 2 decimal numbers corresponding to each place is converted to their corresponding SSD combinations. Right? This is how the code looks like, which means this is what you can implement directly. That means you can go to generate bit stream after this. But because we also want to first check the combination, whether this function, whether the code that we have written works correctly or not, it is important to run simulation as well. So for that purpose, I have written a separate test bench code, and for simplicity, so that I don't have to comment out anything during implementation, I have created a separate simulation source, just like I showed you in the example in the first video, calling it sim2, and here I have a test bench code. This is how the test bench code looks like. A and B are the input variables whose values are going to change, so they are defined by reg. Rest all the variables that we want to display are stated with the wire keyword. We then create an instance of this 4-bit adder to first create the sum, then convert it from binary to decimal, and then call the third module, which essentially gives us the 7 segment corresponding outputs for each of those digits. So we have a few combinations of A and B here, 6 combinations. So this is the code for the test bench, and let us run this simulation and see how it looks like. Our timing diagram looks something like this. So you can see that we can see the inputs A and B, and all the variables that were defined with the wire keyword are also visible here. So I was hoping to view the decimal equivalent of the number here, right? So what we can do here is we right click on the particular variable, say decimal, go to radix and select the unsigned decimal representation of it. So now you can see that it shows 8. We can do the same for each of those 2 digits. So let us take an example of this case. Say I'm adding 0011, which is 3, to 0101, which is 5. So the output is 8, which means carry is 0 and sum is 1000. The decimal equivalent is 8, which means I want 0 to be displayed on the tens place and 8 to be displayed on the units place. So to display 0, the corresponding 7 segment combination should be such that only that middle LED, that is the G LED, that should be off, right? And rest everything should be on. Recall how we had represented the 7 segment combination in our code. From right to left, meaning this rightmost one is corresponding to A and the leftmost one is corresponding to G. Okay, so we are looking from right to left, that ABCD combination. So for showing 0, except for G, everything else is 0. Why is this? Because this is for common anode. For common anode, off means 1 and on means 0. So all these are on except for the last one, which is G. That is going to show us the decimal digit 0 on the 7 segment display. To show 8, all of them are on, right? So this is correct. To show 0, 8, this is the correct 7 segment combination. Let us take another example. So the last one, right? 1 1 1 1 plus 1 1 1 1, that's 15 plus 15. I am expecting 30 to be displayed, 3 and 0. So corresponding to the number 3, what are the LEDs that should be on? What are the LEDs that should be glowing? A, B, C, D, they should be glowing, and G should also be glowing, right? These 5 LEDs should be on. So that is correct. And to show 0, of course, only the G LED should be off, rest everything should be on. So this also makes sense. You can verify each of these combinations. So our simulation has passed the check. This is where we now go to implementing this circuit on the pink board. Now, the moment we speak of implementing, you know that we have to bring in the hardware constraint files, right? And because we are going to use RPI module, in the constraints, we will this time have 2 XTC files, right? So we will call the pink board XTC file and the RPI add-on XTC file. Both have to be added here. So on the pink board, the only change I need to make is for output that is being shown through PMODs. So just like how in the previous experiment, you worked only on PMOD B and you had made the corresponding connections. It is important that here you write the correct variable. Okay, if we go back to the design source, the main design source, remember for the main module, the final module, A and B were the inputs, and what were the outputs? This SSD underscore 10 and SSD underscore 1s. These 7-bit vectors were the output, right? So these are what need to be connected to PMOD A and B respectively. So if I look at PMOD B, this is corresponding to A. So this is pin number 1, pin number 2, 3, 4. Now 5 and 6 are for ground and VCC, right? So then 5 and 6 we skip, we use 7, 8 and 9. These are corresponding ports that need to be connected to corresponding pins on the PMOD, right? So SSD underscore 10s 6, this is the 7th bit of your SSD 10s vector. That is supposed to represent LED A. That is why this is going here. This is for LED B. That was the 2nd bit from the right side, right? 2nd LSB. So this should be written correctly. And how we write this for PMOD B? The exact same way we would write for PMOD A as well. PMOD A will be representing the units place. So we just take SSD underscore 1 and write all the corresponding signals. Now this was about the outputs. We decided to use the RPI module to give inputs. So we double click on the RPI module XTC file, and here we will scroll down and go to switches. Okay, we do not have a separate manual for RPI module actually, but if you look at these the original commented version of these statements, you can see that for each of the pins the corresponding switch name is already given. So SWH, which was the leftmost switch, that was H, and the rightmost switch was SWA. So we had decided that we will give A here, right, in these 4 on the left hand side, and then B over here. So that's exactly how I have defined these A3, A2, A1, A0. B3, B2, B1 and B0. These are the inputs. There are no other changes to be done on this XDC file. We will just save this, and since there are no other errors, we can directly go to generate bit stream. So once the bit stream generation is successfully completed, I'll directly go to Open Hardware Manager, and here I'll connect my pink board, open the target and load the bit stream. So before we load the bit stream onto the pink board, let us quickly make the circuit. So we take a breadboard and two 7-segment displays, put them together like this. I've got the pink board and the RPI module, and you can see how the RPI module fits perfectly on this Raspberry Pi header. We are now going to connect the PMOD to both the 7 segments. So as we decided on the XDC file itself, that PMOD B will be driving the tens place and PMOD A will be driving the units place. So I'm going to connect pin number 1 of PMOD B to LED A, pin number 2 to LED B, and so on, following the pin diagram of these 7 segments. I'll do the exact same thing for connecting PMOD A to the 7 segment corresponding to the units place. Alright, so the bit stream has been loaded, and right now, since all switches are in 0 position, the sum is also 0, 0. Let us make A as 1, the sum is 1. Let's make B also 1, so the sum is 2. Let's make B as 3, the sum is 1 plus 3, 4. Let us make B as 7, so 1 plus 7, 8. Let us make A as 3, so 3 plus 7, 10. A is 7, so sum is 14. Like this, you can try for multiple combinations. So A is now 15 and B is 7, so 22, and both A and B are 15. The sum is 30. So please follow the instructions given in the manual, and I hope you enjoy this experiment. Thank you.